In last class, we talked about our first strengthening mechanism, which is reducing the grain size. And today's objectives include, we want to know other strengthening mechanisms, for example, solid solution, precipitation, along with strain hardening. Strain hardening is also called cold working. And then we are going to talk about recovery, recrystallization, and grain growth. So today's lecture is very, very important, and there's several topics will be appeared in our upcoming quizzes and exams. Now we are going to talk about our second strengthening mechanism, forming the solid solutions. Look at this picture. So impurity. So this is the original items. They make arrangement. They arranged to become. This is material. Suppose we have impurity items. So these impurity item here, and will distort the lattice and generate lattice strain. Here. So these strains can act as barriers to dislocation motion. So these strains will serve as a barrier to prevent the dislocation from moving. So this is a smaller substitutional impurity. This substitutional impurity, impurity generates local stress at point A and also point B that opposes dislocation motion to the right. Dislocation. This is a shearing stress. Right. So this is the shearing stress. So this is the first case scenario for which we have smaller substitutional impurity. Second case scenario is that we have a larger substitutional impurity. So we will have a totally different. Okay, this is a smaller one. So this is the larger one. So we can see on these two corners, C corner and D corner, we will have a strain. So this strain will also prevent this is the dislocations from moving. So this impurity generates local stress at C and D that oppose dislocation moving to the right. So this is a lattice strain around the dislocation. So we can see, so we have this is one plane, this is one plane, this is another plane. So here this is the fourth plane, and this is sixth plane, seventh plane, eighth plane, and ninth plane. And in the middle we have a half plane here, right? So we have a half plane here. And so if we have a half plane here, so these items will be repelling these neighboring items. So they will generate compression here. So this is compression and will be resulted in this area. And however, because this gas existence, so here we will have a tension. So this is a tension. This area will experience tension. Experience tension in this area. So this is then we talk about how we strengthening by solid solution alloying. So small impurities tends to concentrate at dislocations, regions of compressive strain. Okay, we have a compressive strain. I talked about this one already. The partial cancellation of dislocation, compressive strains, and impurity item tensile strains. So reduce mobility of dislocation and increase stress. So here, this is the first one, representation of tensile lattice strain imposed on host items. So this is white circles. They are host items by a smaller substitutional impurity. So suppose this is smaller, then we will have tensile lattice string here. And B, possible location of smaller impurity atoms relative to edge dislocation. So this is edge dislocation, right? So this is edge dislocation, and this such that there is a partial cancellation of impurity dislocation lattice string here. So for larger impurities, large impurities tend to concentrate at dislocations and regions of tensile string, because this one is larger. In this area, we have the tensile string here. And so this is the first picture, is a representation of compressive strings imposed on host atoms. This is a white circles stand for white stand for the host atoms. So B is a possible locations of larger impurity atoms relative to edge dislocation. So this is edge dislocation because this is half plane, and that there is the partial cancellation of impurity dislocation lattice strings. And here, and for this VIMSE solid solution strengthening tutorial, as I said several times, if you have bought this book, and you will have access to VMSE, and then you can just open this tool and to do some animation of solid solution strengthening. So this is very engaging, and you will find, and this one will be very interesting, and you will be engaged and you are motivated to learn this part very well. So for give you an example of solid solution strengthening in copper, so tensile stress and yield strength increase with weight percentage of this nickel. If we have a copper, suppose copper is a host material, host atoms, copper atoms, and we have nickel atoms to have solid solution. And so based on here, so this is the for this vertical axis stands for the pure the copper. You can see, and the weight percentage of nickel equals 0. And for if we keep increasing the weight percentage of nickel, we can see tensile strength increasing monotonically. So you can see it's very impressive. And also the yield strength is also increasing as the weight of percentage of nickel increases. So here is one empirical relationship between yield strength and this is the percent concentration of this concentration, and this is power is 1/2. This concentration, see here, allowing increasing sigma y yield stress and this tensile stress. Any questions so far for this slide? Okay, no question. We move on to our third strengthening mechanism. Our third strengthening mechanism is called precipitation strengthening. So what is the precipitation? The hard precipitants are difficult to shear. For example, so here is the atoms here, and so this is the lattice. Suppose we have a precipitate and here, right? So how can we shear this one? So this guy, if you want, this is original state. So this is suppose, by some means we applied and very high magnitude of shear stress, and then we shear this particle, this participant, this way, and you can see hard precipitates are difficult to shear. It's very difficult. For example, ceramics in metals, and for example also silicon carbide in iron or this aluminum. You can see this one large shear stress needed to move this location toward precipitates and shear it. So suppose this is dislocation. If we want to go through from here to here, you need to to pass this precipitate, and you need to have more shear stress. And so this one, this is the top view. Okay, this is the top view. Dislocation average but advanced but precipitates act as pinning sites with spacing. And pinning sites with spacing. The result is the yield strength is inversely proportional to this is S, this is the space of the precipitates. So here it is S. That means if S, the lower the S is, the higher the resultant yield strength will be. Does that make sense? Physically speaking, it is understandable, right? So the more precipitates you have in this host material, the harder it is to shear this is the material, because more precipitates need to be sheared, and usually they are very, very hard to shear, to be sheared. Any questions regarding the third strengthening mechanism? So application and precipitation strengthening. For example, this is the internal wing structure on Boeing 767. And so aluminum is strengthened with precipitates formed by alloying. So this one, okay, alloying here. Here give you a macrograph of this is the material used in this is the Boeing 767. You can see you have a lot of these dark dots stand for the precipitates. And the fourth strengthening mechanism is cold work. And now let's recap what we have learned. The first one is the first strengthening mechanism is reducing grain size. Second, forming solid solution. Third, precipitation using alloy approaches. The third one is cold work. And cold work is called strain hardening, right? This is very, very important. And also in our mechanical engineering lab, we are going to do several experiments about this cold work and to give you the opportunity to experience how cold work changes this is mechanical properties, especially the tensile strength, yield strength, and also the hardness. And we will have a lot of fun. Okay, so you will like these experiments very, very much. This deformation cold work. This cold means the operating temperature is nearly the room temperature for most metals. And the common forming operation reduces the cross-sectional area. We know that, okay? So here is, for example, here is a forging. This is for forging. We have a die, and we have a blank. Blank is raw material. So this guy is A0, cross-sectional area A0 here. And then we apply the force, and then we have this apply force on top and also bottom, and then we can have this is the final shape and the size. And so this is this blank is the shape and size and are changed, and as a result, this is a percentage of cold work is quantified using this equation. So A0 is the original cross-section area, and AD is the final cross-section area. So the difference between these two guys divided by the A0 and multiplied by 100 equals the percentage of cold work. And for drawing is another example. This is a die, and usually the dies are made of very, very hard material. So this, suppose this is, we can see this is either a plate or this is a rod. If we pull it this way, so this is A0, and this is AD, the final one. And so we can also use this equation to quantify the percentage of cold work, or this is straight hardening. And another example is rolling. Rolling, this is roller, two rollers here, and also here is a workpiece going to be rolled. And this is the A0 is original one, AD is the final cross-section area or the thickness, you can use this equation to quantify the code work. So another example is extrusion. So this is the container. Container are made of very hard material also. So here is a ram. Ram is moving. This when the force is applied. This billet. This billet is a raw material. And you can see this guy will be pushed to pass. This is a very much smaller this orifice. So this is the die holder here. Okay. So this is A0. This is a die. This container. Both container and die, and they are very hard. So you can see, you can imagine if we push the force on this ram, and this is a billet, and will come out in a very in the form of a very small cross-sectional area. So once again, so for this, we can still use this equation to quantify the percentage of the code work, or this is a percentage of the street hardening. So here is a micrograph, and we have dislocation structures change during the code working here. Dislocation structure in titanium after code working. So these dark areas, so dislocation entangle with one another during code work. So this is the reason after your code work, it becomes stronger, and dislocation motion becomes more difficult. Okay, so these are darker lines, and they are dislocation. Dislocation density increases during code working because the volume is changed, right? So dislocation density equals total dislocation length per unit volume. Dislocation length, this is the length. Because dislocation is defined as the half plane. So carefully, the grown single crystal. So this is calculated about 10 power 3 per meter square per millimeter square. And deforming sample increases density. So this is 10.9 to 10 square millimeter. Heat treated reduces density, and it goes back to 10.5 to 10.6 per square millimeter. Then we talk about lattice string interactions between dislocation. So here this repulsion. Okay, so this repulsion. So these two guys, this is attraction, right? So this is attraction. Suppose we have dislocation here in this direction. So this is dislocation in this direction. If this is a two dislocations attract each other, okay, this guy and this guy will become this half plane and this half plane. This is the top half plane and the bottom half plane, and they will form a true plane. So a full plane. So this is a full plane, and that means this is dislocation disappears, and this dislocation disappears. And we call this phenomena is called dislocation annihilation. So this is a preferred crystal. And then we talk about impact of code work. Code work is increased, and we know this is stress increasing, and for these low carbon steels, this is strain. Okay, if this is increases, this is goes up first, and then going down. You can see yield strength increases, tensile strength increases. The tensile strength increases. Also, ductility decreases. So ductility and the strength, and they are competing two competing properties. If for ductile material, the strength is usually low, and for the strong material, the ductility usually is low. The mechanical property alteration due to cold working, you can see what will happen, right? So what are the values of yield strength, tensile strength, and ductility of the cold working steel copper? So this is D0, so this is DD. That means cold working, right? Copper cold working, and so this is a percentage of cold work and equals the cross-sectional area of the original one minus the cross-sectional area of the final one divided by the cross-sectional area of the original one, then multiplied by 100. And so this one can be further described using this equation. And for example, for this specific example, if we just plug in, so this is for this case, the percentage of cold working equals 35.6%. It's very high. Mechanical property alteration due to cold working. What are the values of yield strength, tensile strength, and ductility for copper for different percentage? For the percentage of cold working equals 35.6%. So here, right? So this cold working, so yield strength going up, and so this is the tensile strength also going up, and ductility goes down monotonically for 3 cases. For this percentage, 300 megapascal. For this also the same percentage, we can have this the tensile strength. Also for the same percentage, we know the ductility equals 7%. Then we talk about heat treatment, effect of heat treating of the cold working. So 1 hour treatment of this is at annealing temperature decreases tensile strength and increases this is elongation, so ductility. Effect of cold working are nullified, right? So this you can see this one. So this is ductility. So this is the tensile strength. This is we call so at the very beginning we call annealing temperature. Okay, so this is a recovery. Second one is called recrystallization. Third one is green growth. As the green, we know that in order to enhance this yield strength, the strength of the material, we can reduce the grain size. You can see if we go to the opposite direction, if the grain size increases, we can see the strength goes down. So this is understandable. So 3 annealing stages: recovery, recrystallization, and green growth. These are the cold working. So we talk about these 3 stages. Right? So first one, recovery. And recovery, reduction of dislocation density by annihilation. So this case scenario 1 results from dislocation. We can see this is a plane. So this is called a dislocation. So this is the top dislocation. So this is the bottom dislocation. If we increase the load and so increase the temperature, so these atoms they are moving faster, and then it is very, very possible at some time. So this half plane and this half plane, they become one whole plane. One whole plane means that this is a dislocation annihilation, right? So this is for the case scenario 2. This is this is a shear stress. This is called a recovery. So dislocation blocked, cannot move to the right. This is obstacle dislocation here, cannot move to the right. And the green atoms leave by vacancy diffusion, allowing distance to climb, allowing this dislocation to climb. And climbed dislocation, right, can Now move on next sleep plane. Then we talk about recrystallization. So new grains are formed that have low dislocation densities and are small in size, small size at the very beginning, consume and replace parent cold worked the grains. So here is 33% cold worked the brass. So here is a new crystals nucleate after 3 seconds at 580 degrees C. As cold worked grains are eventually consumed or replaced, so this after 4 seconds, this after 8 seconds. And the third stage is grain growth. So at longer times, the average grain size increases, and small grains shrink, and ultimately disappear. Large grains continue to grow. You can see large grain. So this empirical relationship between the grain diameter at time t minus this is the d0 equals kt, and coefficient dependent on materials and temperature. So t is the elapsed the time. So this is exponential, and this n equals minus 2. N equals 2, around 2. So this annealing temperature. So here is a tensile strength. So this is recovery. So this is recrystallization. So this is grain growth. For this cold worked and recovered grain, so here is new grain, and so here is a grain growth. You can see it is going up. Grain size and going up. Then we talk about recrystallization temperature. So Tr is the recrystallization temperature, and it equals the temperature at which recrystallization just reaches the completion in 1 hour. Okay, so this is a tau r. Tau r is recrystallization. I'm going to test your understanding of this concept. And it is Tr is in the range of 0.3 multiplied by Tm and to 0.6 multiplied by Tm. For specific metal and alloy, Tr, so this is crystallization temperature, depends on percentage of cold working. Tr decreases with increasing percentage of Cw. Purity of metal. Tr decreases with increasing temperature. So diameter reduction procedure. This is the problem. Diameter procedure. What are the consequences of directly drawing to the final diameter? So here's an example. Okay, so this you can percentage of cold working equals A0 minus AF divided by A0 multiplied by 100. So we can get this 43.8%. Diameter reduction procedure. This is a solution. You can see for this percentage of cold working, we have yield strength goes this way, and here is the yield strength and the tensile strength. So this tensile strength and ductility. For this percentage of cold working, we have CMY 420 megapascal TS. The tensile strength equals 540. Elongation equals 6. This does not satisfy the criteria. What other options are possible? For TS is greater than 380 megapascal, and we can have 12% of CW. TS 380. Okay, this is for this brass. You can see here it must be greater than 12%. For elongation, is greater than 15 here, and so this is we can have less than 27%. So okay, the working range is from 12 to 27%. For objective, we need a code work at this one, and we will use 20% percentage of code working. Diameter of the first code work stage is calculated as follows. And so this year we use this equation, and you can just practice of the class. So this is the intermediate temperature diameter. The diameter reduction procedure. Okay, now we just summarize what we have learned. Code work, reduce diameter from 10 millimeter to 8.39, and you can get the percentage of the code work for first the percentage of first code work. And heat treatment allow recrystallization, and then code work and reduce diameter from this one to 7.5, and then calculate the percentage of code work for the second time. And then we talk about cold working versus hot working. Okay, so these both of them are working. And hot working, the deformation occurs above the TR temperature, crystallization temperature, and cold working means the deformation occurs below this recrystallization temperature. Grain size influences property. We know that metals having small grain size relatively strong and tough at low temperature. Metal having large grains and good creep resistance at relatively high temperature. You know creep, right? Creep means that at certain temperature, even the stress does not change. The strain keeps changing. So this is called creep. And creeping is commonly seen phenomena in the metal at a very, very high temperature. For example, the titanium alloy. The titanium alloy, and the engineers found these phenomena, creeping phenomena, when they handled the motor. This is the engine made of this titanium alloy, and they found that even the load does not change, but the strain keeps increasing. So that is how people started investigating